Mm-hmm. Mm-hmm. Niewiele krótcinkie. Okay, let's see what we have a sound. Can you hear me? Okay, can you, Ilya, could you write me if you can hear me and if you can see me? Because I cannot get. Okay, yeah, we're still setting it up. Sorry for everyone. Okay, we're still setting it up. Mm-hmm. Okay, yeah, yeah, just a second, please. Mm-hmm. Так, звук стало лучше со звуком? Окей. Hello, sound improved. Okay, I can see myself on YouTube now. Yay! It's not exactly what I... Okay. Okay, I have a huge lag. Maybe it's normal for YouTube. Basically, I'm saying something and then I'm talking. Okay, we have a huge echo right now. Well, let's see. I'm sorry, guys. I've been told to try to use this technology and it's not that I'm that proficient. Okay, let's try nose gate now. Okay. So let's see if we have an echo. Okay. Okay, how is it now? Okay, it was good before. Yeah, yeah, I'm sorry because I'm getting the signal from YouTube with a little bit of delay compared to what I'm doing something, so it takes maybe a few seconds. Signal. Okay, how is it now? Okay, much better. Uh, okay, Ilya, could you please start writing to YouTube channel because I will be following that and would not be following other sources. Uh, okay. Oh, all right. So Ilya, Vasily. Yes. Okay. So I think we can spend maybe a couple of minutes. Are we waiting for someone else right now? Any? If not, then we can probably proceed from now. Yeah. So Ilya, Vasily, maybe a final clarification. Is it possible to hear this as it is right now? So, is it painful or is it alright? Okay, we can get a few more people. So, while we are still waiting for someone, let maybe me try to get separation actually and disable this gate because now we don't have an echo. So maybe, yeah, just let me know if the sound if the sound improved. Okay, is it better right now in terms of noise? We don't know if it's better or not. Let me try listen for it myself. Right? Okay. Okay, it looks like, oh, looks all right. Okay, great. Great, yeah. I didn't scroll down the chat. All right. So I guess we have everyone who is expected to join, or maybe someone else will join along the way. I'm fine with that. And hello everyone once again. My name is Anton. I am a part of CayleyPy community. We joined last summer, and today I'm gonna present a lecture on Cayley graphs on CayleyPy. How do we look for paths on Cayley graphs? So this is somewhat an intermediate like introductory intermediate lecture. So I am not assuming way too much knowledge, way too much prior knowledge compared to like, so I guess I'm just expecting you to have some basic maths and machine learning and programming awareness, and I will try to give all the necessary details. And feel free to ask questions to the chat. I will be reading them from time to time, and will try to make some pauses uh, to address your questions. All right. So, uh, by the way, uh, so this is somewhat like a recap of the lecture that we had in December, even though it's like in English and the last one was in Russian. So, uh, for those who haven't been on the last lecture, there is a small puzzle. Try to guess. So look at this graph and try to guess. Are you familiar with the group that graph corresponds to? It's okay if it's unfamiliar. I'm just curious if anyone could guess. But if you have been in the last lecture, please don't reveal the answer. I don't know if we have Alexander here, who is a driver of like a main driver of a community. So Alexander, if you're here, please don't answer. You did it last time, I remember. And yeah. Okay. So I don't see the answer yet. Yeah, so feel free to write it in the chat. But I will proceed from now. So our plan for today is, so first I will give some introduction to Calligraph, I'll give the definition, show some examples, then we will address some pathfinding method. I will do a really quick review on classic approaches, then we will talk in a little bit more detail about beam search, then the pinnacle of the lecture would be predictors, how we can trade them, how we can use them, and then we will jump to the conclusions. Okay, somebody had triangle flips and rotations. Well, I don't think so. I think triangle flips and rotations has a little bit more. Or maybe. But actually, well, I think not. But I'm curious to try if it actually works here. Maybe. But yeah, originally there was a different group. So let's begin with calligraphs, and I will give somewhat of a loose definition. So if there are any mathematicians in the room, please bear with it. I like to think about calligraphs in the following manner. Imagine that there is a system which has a notion of state and a transition between the states. The transitions are assumed to be deterministic and guided by actions, and we will also be calling actions as generators. Given such a system, one can map the states of the system to the nodes and transitions to the edges. And well, once anyone has a set of nodes and set of edges, that's a graph. We usually assume that in our systems, transitions are reversible. So if you get to one state from another, that by some other action you can get from another state to the one you got from, which makes our graph undirected. And then all actions are allowed in all states. It's, for instance, would not have been true in chess. Then not action in chess are allowed in any state of the chessboard. But in the systems we are considering, all states are allowed. All actions are allowed in all states, which makes our graph regular. So each node has the same amount of edges coming out of the node. Then we assume that all our states are reachable, which means our graph is connected. So there are no pieces which are float connected to each other. And in addition to that, we also assume that there is a state called the central state. It's kind of a special state. It's usually no better, no worse than any other state, but we consider it somewhat special. So when we're talking about Rubik's Cube, it's usually the state where the cube is in its like original state where all the tiles have the right position. So if it's like something related to the permutations of the string, that would be considered an ordered string. Well, as you might know, that many books and many sources define calligraphs in the context of a group theory, which is an algebraic structure. Then it's also totally legit to think about our Cayley graphs. By our Cayley graphs, I mean the things which are considered in the scope of this lecture. So it's totally legit to think about Cayley graphs in the context of group theory, and one can study one by studying another. And of course, any group can be mapped to a Cayley graph. Well, another way to think about Cayley graphs is to think about how the Cayley graph can be built. Well, again, assume that there is some state called a state space, some space called the state space, and then there is a single state in it called central state. Then we have a group of operators defined which are acts which act on its space. So each element of the group takes an element of the space and maps it to another element. And we also consider this group has a set of generators. Generators is such an elements of the group which you can basically compose any element of the group by combining the operators. And we usually consider the generators there like the most interesting for us. So once having that, take your central state and apply all the actions from the sets of generators. Once it's done, you'll probably get some new states. Add them to the graph as well as the edges you get along the way. Then repeat the process with new states, get states once again, then go on and go on and go on until all states are reached. Once it's done, then it's a Cayley graph. So one can say that the Cayley graph, that we build Cayley graphs when by repeating this process, new states stop appearing. Yeah, and again, it's more or less similar to what I've told before. So that's another way how to think about Cayley graph. Yeah. Now let me jump to some examples. The first example is LRX, and that's example from the title page. The LRX is a pretty simple group. So first, assume that the state of the space of states is a space of a string of strings where each letter of the string is a different letter. So basically, it's this letter can be numbers from 0 to n minus 1. Then our generators are left shift, so the whole string kind of shifts to the left, then right shift, so the whole string shifts to the right, and X element which swaps zeros at the first element. And it's quite easy to prove that in this, so that it's possible to achieve any possible permutation of a string by applying only these three operators. A question to the chat: can anyone quickly sketch a proof why all permutations can be reached with these three elements? Maybe not a rigorous proof, but something like a sketch. So how is it possible to get any permutation of a string applying only these three operators? Or like, why is it possible? Yeah, I have to make some extended pauses because of the lag between YouTube and the actual physical reality happening here. Okay, any sorting can be achieved with neighbor exchange. Yeah, that's correct. That's basically, so these three operators, by shifting all by shifting the string, so say you want to exchange element number like 10 and element number 11, so you shift the string 10 elements left, you do the swap, and then you shift it 10 elements right, and then two adjacent elements are swapped. And once you can swap any two adjacent elements, you basically can implement a bubble sort, and bubble sort sorts any array of like any array of any size, which means that reversing the process of bubble sort, it's possible to achieve any permutation. Yes, pretty good. Then let's consider another example, actually two examples. Yeah, so about LRX, you can see that LRX actually grows pretty fast. So on the left, there is a LRX of 3 elements, which is only like this, strings of 3 letters, not a lot. But once we get 4 elements, we already have 6 layers. So the layer is a set of nodes which have the same distance to the central state. With LRX5, we already have 10 layers. Yeah, for LRX4 we had 7 layers. Sorry, I misspoke. And then this group goes pretty fast. So beyond like 5, I would say it's pretty tough to visualize. Maybe 6 is alright, or 7, but it gets tougher. It gets tougher and tougher. Yeah, then there are 2 other examples which look way more messier. They're called reversals and transpositions. A group of reversals, they're also defined on strings, but here a given string. So a reversal is basically a flip of a substring of the string. So and in reversals there are quite a lot of generators. So any substring can be reversed. And transpositions, I think they have also quite a lot of operators. They even more than reversal. So they take 2 substrings which do not intersect and they swap them. And by similar reasoning as in LRX, both groups can achieve any given permutation, but the difference between them and LRX is that those graphs are way, way denser. And that's easy to see why, because there are so many generators that the states of the graph can be reached faster from the central state, just because there are like more ways to reach them, and consequently they have less layers. And again, so maybe just take a look on those two. Those transposons and reverses are defined on the strings of length 5, not so long strings, and that's how on the right how LRX 5 looks. So way different. It goes way further away in terms of the layers, and each layer has way fewer states. Yep, that's yeah, and I'd say that's an important lesson from here, that probably the size of the state itself does not matter as much as the choice of generators. And again, the state of the state matters in terms of that there are many generators that can be, so that the bigger is the state size, the larger is the graph, so the harder it is to work with them. But I might argue that a set of generators is what truly defines the structure of Cayley graph. And I would say that's the most important question when you decide which group you are going to work with. And then another example, the last would be Rubik's Cube. That's somewhat, I guess, closer to everyone who, like basically somewhat closer to everyone compared to LRX. I'm not sure if anyone have heard of LRX before studying Cayley graphs. So in case of Rubik's Cube, its states can be considered as vectors of length 54, but now they're not unique. The elements are not all unique. They are grouped into 6 groups, which we as humans usually call colors. And the moves represents the rotations of the faces of Rubik's Cube. And because it's possible to flatten the whole Rubik's Cube and mark all the tiles, of course, these moves, those physical transforms of the puzzle, can be represented as permutations. And yeah, and that provides us with the opportunity to work with such system numerically. Here on the right, you can see the Cayley graph of Rubik's Cube, but only first 3 layers, because the full Cayley graph has about like 10 in the power of 19 nodes. That would be pretty hard to visualize. Well, let me make a quick stop here, and could you please tell me if there are any questions regarding the examples or regarding the definition of a Cayley graph? is there anything you want me to address right now? Yeah, I can scroll across the slides just to keep everyone entertained while someone is coming up with questions. Oh, that was a step forward. It's all right if there are no questions. I expect that this part should be pretty clear, but I still wanted to do this recap to make sure that we are on the same page. All right, I don't see any questions in the chat. Great, let's proceed. So now let's go to the second part of the lecture, which is pathfinding and quick, really brief recap of classic approaches. So first of all, what's pathfinding? Pathfinding is a problem where given a state X, uh, we need to provide with an algorithm to find the path to the central state. And again, one can tell that we can just look for paths between any given states. It can be done by reassigning the central state, and in our context, we usually find paths from a given state to a central state. And the context of Rubik's Cube is pretty natural because for Rubik's Cube or for other puzzles, our central state is when the puzzle is assembled, and we usually want to get a set of moves from a given state, from given positions of the tile to a central state. Ideally, we want to look for the shortest path, but it's not always possible or easy, so sometimes we have to be happy with just some path. One approach which is pretty easy to come up by, called breadth first search, BFS. It works. It basically works like a search on the graph. So we take one of the states, either target or central, and then we take all the neighbors, check if any of the neighbors is the state we are looking for. If not, we continue to get the neighbors and look for there until we reach our state. And it's easy to prove that by this process, eventually we will be able to get to make a lookup through the whole Cayley graph. But of course, this approach is extremely memory greedy, and in any real situation, or like depends on how real the Cayley graph is, but for any like reasonable puzzle, BFS does not work really well. It's just too memory greedy. Maybe only for the smallest puzzles they can be fitted into the desktop. There is a modification of BFS called bidirectional BFS, where a similar process starts from both target and central state, or both initial and central state, and then we are looking for the intersection. So this is like slightly faster and can be optimized a little bit better, but still quite greedy. Then there is beam search. It requires some heuristics and does not guarantee a shortest path, and we will look into beam search later because it's quite important to make a connection between machine learning and pathfinding through this algorithm. Another algorithm which you might have heard about is A star, which is actually capable to provide us with a shortest path, but it requires admissible lower bound heuristic, a special kind of heuristics. So this heuristics, this way of analyzing something about the states, has to be found for each group separately, and usually a matter of using A star is a matter of whether one can find that. There is a variation of A star called Ida star. It's like a star but consumes less memory, and another noticeable example is Korf's algorithm, which is Ida star with lookup tables. So lookup tables are used to construct these special heuristics. And if I remember correctly, Korf's algorithm was an optimal solver for Rubik's Cube. Well, we're not gonna go. Well, I think this bidirectional beam search exists, and it's also possible to do so. So this list is not an exhaustive list of all possible approaches, and each of these approaches can be optimized. Yeah, that's just something I I decided to put on the side to give a gist of how these things can be naively approached. But yeah, of course, it's valid that beam search can be used in a bidirectional sense, though there actually might be some problems. But I think yes, I think it's possible. Okay, so let's go on with beam search. Well, it's quite a lot of text here, but actually it's quite simple algorithm. So now consider that we have an initial state and a central state, and we need three pieces to make this algorithm works. First of all, we need a goodness predictor. A goodness predictor is a function which takes a state and tells how good it is. How good in terms of how good it is to how close it brings us to the central state. Say inverse distance from the central state would be a really nice goodness predictor. And this is a heuristic. It also has to be constructed for a given group, but beam search assumes that we have it. Then there are two parameters: beam width and maximum steps. Beam width is a number of threads we are maintaining. More about it in a minute. And then maximum steps is just how many iterations of this algorithm we allow before we give up. Well, let's maybe go to the graphical visualization of beam search, and then I will show this text once again. So what's actually happening? In beam search, we take an initial state, then we get all the neighbors of the initial state, and we evaluate their goodnesses. Then, yeah, and moreover, now we have basically several paths for which we have already checked. Then we check if we already explored more paths than our beam's width. If it's more, then we truncate the path with the lowest goodnesses. If not, we take all endings of our paths and get their neighbors, evaluate their goodnesses, truncate, and we go on and go on until either we exceed the amount of steps or we reach a goal state, a central state. So in this example, there are two threads, and in reality, it's usually way more than that. But yeah, that's a limitation, and it turns out that beam search works really well when it works pretty well when there is a good goodness predictor, and also can be amplified with increased number of threads or like beam widths. So that's maybe a little bit more formal representation of it. So we set in a buffer of a paths and goodness of the last element of the path. We set counter to 0. Then we take initial state, put it as a path of a single element, calculate the goodness, put it into the buffer, and then we go into the loop where we take all paths from the buffer, take the last states, evaluate the neighbors, get the goodnesses of the neighbors, and populate the paths, add them to the buffer, and check if the buffer is exceeding the beam widths. Then we truncate the buffer to the beam widths, and we also check if we have reached reached the central state. If so, then we return the path. If not, that we proceed until we either reach it or exceed the number of steps. And of course, there are like many modifications and many improvements in terms of memory, in terms of speed of beam search, and there are like many. Some of them are like more fundamental, others are technical. I would say they're not really important for the scope of this lecture, but what's important is that here we use we see how some predictor of the distance or some other like good value can power a pathfinding algorithm. So are there any questions about beam search? I would say this is pretty important bit. We are not going to use beam search a lot throughout this lecture, but I really want it to be in your heads so we keep our story connected. And if so, please answer me. If say I have how many symmetry in 333? I do not properly get this question. I'm sorry. And okay, and then maybe questions to the audience while somebody are coming up with their questions. So imagine that we have that as a goodness predictor we use inverse distance. So we somehow can connect beam so we can calculate the distance from a given state to a central state, and we know it's always correct. And imagine that our maximum steps is like large enough, so larger than the diameter, way larger than the diameter of the graph. Do you have any intuition how large should be beam widths in order to use beam search to achieve the central state? And would the path be shortest if we have a goodness predictor, which is an inverse distance? Or are we guaranteed to achieve it? And meanwhile, Renuka, yeah, feel free to ask your question once again. I just didn't get it, but maybe if you ask it differently, then maybe I can address it. Yes, okay. Yeah, beam one will suffice, and will the path that's true, and will the path be the optimal, the shortest? Yeah, we get the shortest path, so that's true, and that's so if only we could have the ability to calculate distances to the central state, then beam search would be really optimal, really nice algorithm. But it doesn't mean that beam search is so nice and such a smart thing. It just means that it's basically addresses puts all heavy lift into the goodness predictor, and our beam search is usually as good as our goodness predictor. All right. Well, since we need a goodness predictor and we know that it should be connected to the distance, let's see how can we train it. I will be addressing two algorithms here. One of those would be, and this is the first one, which we call random walk regression. I don't think it's an official name. You can call it anyhow you like, but the idea behind this algorithm is really simple. First of all, sample random walks. Take a central state and just sample paths by randomly walking over the graph. And then for each state in your random walk, use the number of steps inside the random walk as an estimate of a distance from this state to the central state. Then compose a dataset of a states and their estimate, and fill the model, any regression model you like, to predict those estimates. Well, the advantages of this approach is it's really, really simple. I don't think I think like anyone who did any machine learning course can and has an engine to generate the graphs, or like can come up with an engine, then it's pretty straightforward to do that. And then of course these four steps can be like repeated as many times as one likes. Usually a single iteration is not enough. But then the biggest disadvantage evidently is that this approach will work only in a small area around the central states. Why is that? Let's look at some experimental data. So here we have two groups, LRX9 and Tetraminx. I think both of them can be actually fitted inside the desktop memory. That's why I can, for any given state, I can do the BFS and get the true distance. Yeah, so, and let's see the simulation. Here you can see, so first look at the middle graphs, which are named vanilla random walks. Here the black dashed line, which is line x equals to x equals to y, is our estimate of a distance which are given between random walks. So we just say that okay, each step should bring us exactly one layer away from the central, which is of course not true for random walks, but that's our simple estimate. But then the blue line here on the top is a diameter of the graph, so the maximum distance ever possible. And then those colorful wiggling lines are distances which are got through some random walks. So here in the middle, you can see that pretty soon, depending on the group, but rather sooner than later. Our random walks tend to, so our random walk estimate, our black line, tend to largely overestimate the true distance. And that's pretty natural because our random walks are not obliged to move away from the central state. They go whenever they like to go, and they usually tend to get to some typical radius and wander around it. You can see it especially nicely in Tetraming's group. Well, there is one obvious improvement to random walks which can somewhat amend the situation. They're called NBT random walks. NBT stands for non-backtracking. In these random walks, we are not wandering randomly, but for each random walk, we track the states we have already visited, and if our state coincides with the states we have already visited, then we never go back there. And of course, these random walks, they tend to bring us further away from central state, and you can see it on the right. Or actually, yeah, there is one plot which you probably can't see, so I will move my camera maybe here for a moment. Yeah, so you can see that this yeah, you can see. So you can see that these non-backtracking random walks, they indeed get us further from the central state, and they stay on this estimation line longer compared to the vanilla random walks, but still they have the same dynamics. At some point, they get to this typical radius, and they wander there. And that fact limits the applicability of our random walks regression. So first of all, what we can already see that so that if we want to train our predictor that way, we have to. There is no use in sampling random walks further away. We don't really want to go far from this nice ball where the random walks are somewhat closer to this black line. Why don't we want to do that? Because once we get to this asymptotic line, our data is mostly noise, and they will not provide any useful information to our predictor. And indeed, when we try to train our models like that, we found that if the random walks are too long, that the quality of the predictor drops, and that's pretty natural. And second, this predictor being trained like that, it will be functional only in some vicinity of this central state. So usually when we plug it to beam search, we have to set quite a wide beam. And what's actually happening between beam search, or at least what it feels like, that once we start our beam search, we first wander always randomly because our predictor has no idea what's happening far from the central state. But once any of the threads gets close enough to the central state, it immediately falls there. And that's why I believe that's why this method is actually working. So yeah, but funny enough that this method is somewhat functional. Okay, there is a question if there is so there is a question if there is any theorem about how was the distance of random walks on the graph. Well, it largely depends on the graph. So for d-dimensional lattice, I think it's not always a square root of n. It's like it also depends on the dimension, of course. But yeah, I think for some dimensions it's like square root of n. Yeah, and then yeah, so it's basic, and again, and also d-dimensional lattice is also a Cayley graph. Yeah, so for that particular Cayley graph, this statement would be correct, but it usually depends on Cayley graph. For instance, if we would have had a tree graph, I'm not sure if Cayley graphs can be trees, but if we just consider the same as a tree graph, Then, of course, random walks on trees, especially non-bad checking random walks, they provide the correct estimate of the distance because they never come back. But we are not really walking tree graphs. Another question was, will this be posted? Okay, there is a like button, so I cannot see. Will this be posted for the review afterward? Well, I'm happy to share these slides, and I will hope that we will have a recording, and we will be also having a small Q&A section after the election. So everyone who survives that far, then you're welcome to join. And of course, yeah, you could look through the slides and see if you can get more of it. All right. So, are there any extra questions about this particular method? So, did you mention lattices? What do they look like? It's basically just so imagine, say, a nodes are aligned with a square, so imagine this kind of an infinite square lattice, like the nodes in the which composes squares, and that goes infinitely. It's basically like a grid you can see on the graph. So yeah, it's somewhat like pretty natural. Yeah, all right. So I'm just giving a small pause to like wrap your thoughts together, and please ask any questions if you have about this method. It's pretty basic. It's not sophisticated at all, but of course, if it's like a lot of new material, it's maybe a good place to stop and ask something. Well, all right. I can't see a lot of questions so far. Maybe it's a YouTube bug, maybe not, but I think we can go on at some point. All right. So now, given that this method, let's actually consider something more sophisticated, and that's training with reinforcement learning. So first of all, I will provide you with this algorithm. I will explain how it works, and then we will dive into details, into some theory behind it, why is it actually working, and what's pros and cons of this algorithm. So first of all, the beginning is the same. Sample random walks starting from the central state, but then for each state get some Bellman targets. How to compute Bellman target? Well, for a central state, Bellman target is simply 0. Then for any other given state, one needs to get all the neighbors of this state, gets the values of our predictor in these neighbors, gets the minimum, multiply by gamma, and add 1, the second line in this braced equation. So again, in order to compute Bellman targets, we used our predictor, and it's totally fine that our predictor may be initialized as a set of random numbers or just a random neural network. We don't care much in this case. What we do, we just compute Bellman targets with this procedure, and then on step 3, we regress our predictor to Bellman targets. And then we go on to step 1 until our predictor converges. So a really important point here that for this process, we don't use any external estimates. We don't assume anything about anything about the states and their distances. All right, yeah, I think my head overlaps a little bit. Thanks. That should be better. Yeah, okay. So for this method, we do not consider any estimates for our states. We don't care if so we don't care if our graph is like what it is. We just do this procedure and hope it's to converge. And that's the biggest advantage of such approach, that we basically use only the graph itself. The concept with this approach, it has some stability issues, and in a moment I will tell you where they're coming from. So first of all, let's dive a little bit into the theory, where this Brest equation is actually coming from. For the moment, forget anything about machine learning. Forget about, okay, yeah, just forget about machine learning. That would be enough to forget. Consider this. Imagine that we're just solving some equations on a graph, and let's solve this system of equation. That's basically the same as update, but yeah, we have some function which should be 0 in the central state and should satisfy this equation, the second equation for all other states, where the minimum is taken over the neighbor of a given state. Let's consider first the gamma equals 1. So if gamma equals 1, one can prove that this system has a solution which is a distance function. So if you just plug distance into this equation, you can see that distance will satisfy those. Then there is a proof of uniqueness, and the proof of uniqueness is done by induction over the layers. So you just assume that there are two different functions, you split the graph into the layers, and you assume that it's true for the given layer, and then out of that you can prove that those two functions would be coinciding on the next layer, and by the mathematical induction you just prove it for the whole graph. For gamma less than 1, the function is a little bit more complicated. It's still a monotonous function of the distance, but now it's somewhat like a sum of geometric progressions, because what's happening there, that each one you step away from the center, you're not adding 1, you're kind of adding 1 times gamma. Yeah, maybe don't really try to stack your head too much about that. It's not really that important. The important bit here is that this case gamma equals 1 is also solvable, just a little bit more of mathematics. Well, so now we know that if we have this system of equations and we can just solve it on a graph, then we can get a distance. And if we can get the distance, we can use our beam search, and that makes us, for some reason, like very, very happy. All right. How can we solve this equation? First, let's assume that our graph is small. It's so small that we can actually use our function we are solving our equation for as a table function. So we just initialize it with random numbers, and then we iterate. And then we compute the right hand side of the equation with those random numbers for all states, plug them back into the table, and repeat process over and over and over again. This algorithm is called value iteration. You can find it in many classical books, I think on control theory, or like some on reinforcement learning. And there are actually mathematical proofs that this process will converge. For gamma less than 1, this operator on the right hand side would be a contraction on the state of function, and then there is a Banach theorem which will tell that, okay, each time you get, so first this operator will be having a fixed point, and its fixed point is the solution of the equation, which is a distance function, and then each time you apply this operator, you will be getting closer and closer to this distant point. For gamma equals 1, this theorem does not hold, because it will be contraction only if gamma is less than 1, but there is still proof that this system will converge, even though now I think you have to initialize the table function in a special way. If I remember correctly, you need to set it to 0 in the central state, and somewhat like infinity, or like reasonable infinity, or like reasonable infinity on all other states. There is a question to the chat. The table is populated with any random numbers. Is there no bound? For gamma less than 1, yes, there is no bound. Of course, if they're like, there is a reasonable bound if you can get any estimate about the diameter of the function, or diameter of the graph. Then of course you probably want to populate those below the diameter, below like the upper bound for the diameter. But what's nice about gamma less than 1, yeah, that this process should converge to the fixed point, which is the solution of the equations. But for gamma equals 1, yeah, the initialization might matter. Well, okay, so looks like we can solve our, so we can basically find our distance for any given graph. So why don't we just use this algorithm? What's the problem with that? Yeah, that's a question to the audience. Yeah, and while you're answering the question, there was a question before how you paint graphs so accurate. Well, I just have some Python functions to generate those graphs and provide the layers. I have something in my like public repo, so you could probably find it there. They're not properly documented. Sorry for that. Yeah. So, but what's the problem with this value iteration? What prevents us from using it for any Cayley graph we want? Yeah. So first of all, we need to iterate over 10 in the power of 19 nodes for Rubik's Cube, and Rubik's Cube is not the largest puzzle one can imagine. So yeah, that's one problem. And another problem, which comes even before that, that for some large Cayley graphs, we could not even maintain this table. It just would be too much of data. And trust me, it's more than possible to come up with a Cayley group which for which even the table would be impossible to keep. So yeah, this method works only for the small graphs. But there are ways to amend this, and this method called approximate fitted value iteration. So first of all, well, the graph is large, and we can, and imagine that we don't really want to keep the whole lookup table. Well, let's fit an approximator. So instead of uh, keeping a table, let's use some neural network, and then can even come up with some unexpected bonuses. But yeah, that's all the problem about keeping up with large tables. And then so that's where the word fitted is coming from. Then there is another word called approximate, and this approximate coming from the fact that now we are not going to look up the whole graph, but rather through a subset of the nodes. So we just sample nodes out of this graph and do this value iteration only with a subset of nodes. Now, if you plug both these pieces together, you get exactly to this process. Let's check it out once again. Yeah, let's check it out once again. Our random walks are just a sampling algorithm. That's how we just get some states out of our graph. Then for each state, we do the Bellman updates, which is exactly our value iteration. Then we regress our predictor to these Bellman targets, which is basically the same as updating the values in a table. And then we repeating the whole process because we probably would not get enough coverage, and we need and even with the table we need to get some iterations to get it working. And here you can, and of course all our nice theory and all our nice theorem which will guarantee us that our process will converge, they are not working in this case, simply because we are not looking up through the complete graph. For large groups, there would be easily some places where we never look up, and of course I would say there is no feasible way to make our function working well in this case. But there is some hope. So first of all, because of the stability issues, because these convergence guarantees are lost, that's why sometimes these processes get unstable. One thing that we actually need to do is to make sure that our sampling is as dense as possible. And there would be regions, especially with random walk sampling, where our sampling is dense. Say around the central state, we usually get almost all states, or like most of the states. But once we get further from there, we are not getting there way too often, and the quality of our predictor drops. But the nice But the nice bit here that eventually we can sample it not only by random walks. We can say imagine that in our group, like in LRX or in transposon, uh, we can just sample groups by providing with random permutations, and random permutations are even cheaper to generate than random walks. So eventually we can just plug those extra random permutations, and because all these Bellman targets are updated jointly, there is a hope that our function will probably get more global structure of the graph. And there is another hope. Yeah, and sounds a lot like machine learning talk because we don't get any guarantees. We get a lot of hopes and like these generalization ideas. But yeah, we actually believe that if our function is not too big, that it might eventually get some patterns uh, if the states are represented in the correct way, and then it will actually work better in not only on the states it has actually seen. But of course, there is no easy way to prove it. So that's approximate fitted value iteration, or also we sometimes call it just training with RL in our community. But of course, RL is like bigger than that. But I'd say it's another good place to make a pause and to ask some questions, because I guess that's the most complicated part of the lecture. Yeah, so while you're coming up with a question, once again, first of all, we prove that this system of equations gets the distance. Then we found some theorem which saying that treating this system of equation as an operator applied to the function and applying it multiple times, eventually we will converge to the true distance. And then we say that because our graph is too large, we have to fit the approximator and use only a subset of nodes. So how do I choose a subgraph? Well, eventually we don't have much of a choice. It depends on the group, but one way to choose a subgraph is just to sample random walks, because when you sample random walks, you naturally get a subgraph graph. Another way is to sample random permutations, which would be a terrible choice, probably a terrible choice for puzzle groups, because in puzzles, not all permutations are allowed. So you need some way to know which are allowed, which are not. If you can do that, then yes, of course you can just sample them randomly. But basically, and I would say a choice of random subgraph is a smart choice of random subgraph may improve the convergence, and the easy target here would be density of the sampling. So ideally, we shouldn't sample in some regions densely and in some other regions not densely, but we would rather want to make it like spread it. But of course, we cannot always control it. Isn't the value iteration which is on an operation, but n is mm, I actually don't think so. I'm not sure if so. You mean that fitted value iteration? I mean each iteration is of course, yeah. Each iteration is of course is O10. I mean we have to look up through almost, not like the whole. So not the number of iterations, but each iteration itself. Yeah, and that's why it's unfeasible for the large group, we will have to use a small chunk of those. That's correct. Yeah, and that's why nobody does value iteration on any large Cayley graphs or like on any real reinforcement learning system which has an analog of this process. It's just infeasible to keep track of. Yeah, and that's why we are doing subsampling. So that's why we are choosing some subset of the nodes. All right. So feel free to plug more questions here. And there would be like just a few more bits of information, and then we will be wrapping up to the Q&A session. So first of all, some possible improvements of this algorithm, which are quite easy to come up with. One way is it's actually possible to use maximum function, I think with minus sign, if I'm not mistaken, alongside minimum function, and in some experiments it worked. I think there are some problems uh, with plugging the maximum function in terms of mathematical like beauty, but it still like actually makes some sense. Then yeah, okay. There was a question about why does that work? Well, okay, yeah, I will get to the questions later. I will first go through the improvements. So first of all, big or small model. So using max outside minimum, yeah, that's covered. Then another question is whether we want to use our predictor as a large model or a small model, and balancing between the size is quite important because large model is capable of just memorizing the states better, while a small model arguably would be generalizing better. So I guess for each group, it's kind of a choice. It has to either be tuned or guessed or chosen somehow. Then, of course, using different architectures like possibly transformers, GNNs, equivalent nets might be beneficial. We actually haven't used everything that comes up into one's mind, just because not everyone has enough time to try everything. But yeah, of course, there is some hope that some smart architecture, which eventually you just need to take some representation of the state and regress it to a number, and maybe your architecture would generalize better. Then, of course, various sampling approaches should be tried. That instead of sampling from the central state, it's possible, say, to look for some states and then use them as seed state and then sample random walks of there. So do some combination of random walks or do some combination of shallow and deep random walks and see how it works. So that's also works quite well. Then another thing which is also possible to do, that right now we're usually trying to get the distance predictor and then plug it to beam search, which is pretty straightforward. And again, yeah, in any real Cayley graph we've tried so far, this approach does not give you an actual distance. It gives you some predictor, which is not always working really well, and it usually works well about the central state. But imagine that this predictor would be also updated, so we're using the same value iteration during our Q-learning. And that might be beneficial because we are kind of jointly updating our predictor about the states near the center and about the states where our threads are currently are. So this is somewhat close to Q-learning algorithm. If you have studied reinforcement learning, that might ring some bell here. And of course, there are like way how to experiment here. Then another thing which I also believe might be quite valuable is uncertainty estimations, that when we are sampling and when we are like sampling the network during training or during inference, we usually sample just uh, so we usually sample just by the distance itself, but we can also use some methods to estimate how certain our system about its own predictions and use this information to guide our sampling approach. And then there are some other projects like uses asymmetric losses, because our distance usually have some biases which can be detected, and these asymmetric losses can are meant for these biases, and I guess there are way more ways to improve. All right, there was a question. There were quite many questions here. That's good. And the last question was about visualization. I do have some visualization, not a lot. So first of all, there's some training artifacts. And on the left, you can see here how this Bellman loss, so this discrepancy between the Bellman updates and the targets behaves. For some reason, I think I've seen some mentions about why it can be, but I don't really know why. It first drops really fast and then goes up and then starts slowly going to the asymptotic value. And actually predictor gets good while getting away from this so it's not really good around here, but it gets better while driving through this asymptotic thing. This is a validation and chain loss, so I usually keep some states for validation in order to account for overfitting. And yeah, and then on the right, that's somewhat maybe close to Vasily is asking. So for some group, it's actually a larger group called IHES. It's like a Rubik's Cube, but it's a variant of a Rubik's Cube, and this IHES is bigger. The calligraph is bigger than a regular Rubik's Cube, but it's still possible to get some information about shallow states. And we can see that even with this approach, which should not converge on the whole graph, near the central state, it works pretty well. So here you can see for each distance a distribution on the predictions, and the cross is at the place where these distances should be. So for 0 states, for states which are like 1 and 2 step and even 3 step behind, all our estimates get really close, almost they're providing almost the same value as they should. And then while the distance grows, our predictors start getting more variance, which is, I guess, again, more it's somewhat expected. Oh, all right, yeah, my camera is away, blocking the view. Now let's move it here. Yeah, so yeah, so on each step, on each distance, we basically get a little bit more variance, because once we get in further from the central state, the density of our sampling drops, and then eventually our estimator gets worse results. A good thing about these estimators is that even though we're not getting the true distances, they're still working well if they manage to order the distances. So again, even within the first, and we see that even with these variances, that the states are mostly ordered well. And of course, there are some overlaps, and those overlaps will grow while we're getting further away from the central state. But again, within some ball around central state, it's better. And it works quite well. And what's nice about this approach is that there are ways to extend it to like amplify it even before this simple fitted value iteration. And I would say, yeah, that's it. I would also, by the end of this slide, provide some useful resources. This is a Sutton Bartow's book on reinforcement learning, when you can get some ideas about reinforcement learning in general. Then there is a book of Verticas, network optimization. There you can, for instance, find the proof of the convergence for gamma equal 1. And I also I also recommend you to check out deep reinforcement learning course from Berkeley, guided by Sergey Levin. And this course is also like kind of deeply mathematical. So it's deep both because it's about deep learning and reinforcement learning, and because it's both quite deep and quite wide. So yeah, it's a really interesting thing, and they have online home tasks which you can just self-assign yourself, and they also have YouTube lectures. Also, we have our community, which is CayleyPy community. You can check our GitHub. You can check our list of our Kaggle competition, where you will find some tests or notebooks where you can actually try those methods yourself and then probably improve them, see how your method compares to the other scores. I will probably open this Kaggle later on. And this method, there is a notebook which uses this measure on IHES. It's actually where those charts are coming from. It's available with this link. So that's it for the lecture, and now we are getting to the Q&A session. There are a few questions here in the chat. So we'll start addressing them now. All right. Why does this work? Well, in like all machine learning, it shouldn't, but sometimes it does. So eventually, what's with only these methods, what happening is that we're getting a decent predictor near the ball, some ball around the central state, and then we plug it into beam search and hope that one of the threads will actually get to this ball and then it converge. But arguably, with this method, we can get like a wider ball and maybe more dense sampling and like more reasonable predictor compared to the com, com, compared to the random walks regression or like some other methods. And then of course, yeah, and then of course there are like many things to try here. Okay, I'll graph an end use for this. I'm concerned about whether an end will really work well if the graph structure is not encoded. Well, graph an ends is definitely something to try, and unfortunately, I haven't seen these attempts in our community so far, but it's pretty straightforward way to go. So yeah, if you're familiar with them and you have time, at least, so one kind of easy way to go on with it is just try to for this like predictor, not using like multi-layer perceptron, but just some graphical or like some graph neural network and see if it works better. But of course, you will have to account that on the speed of the speed. So sometimes like a more advanced architectures can be like either worse optimized or like just heavier than light architecture. So there's always a balance between how much you can sample and how much iteration you get within a given time frame compared to the actual quality. But yeah, graphical neural networks is a good idea, and maybe there are some methods within them which are not fitting this framework. So yeah, if you come up with something that works, please try. That would be really interesting, and we'll be happy to see you. The same, I think, applies to GraphLowNet. Do you have visualization some learning distance using aerial similar to visualizing of regression? Actually, yes, Vasily, I have it. Let's maybe try jump into the Kaggle notebook of mine. Let's see if I can actually open it here. Yeah, so the distances which we are learning. So yeah, this is Bellman training. Okay, that's shouldn't probably log it that much here. Yeah, so the learn distances, yeah, they're somewhat like this. So yeah, they behave quite similar to what they are for networks, but of course, it doesn't mean that they're actually predicting right distance, like correct distances. But yeah, they look reasonable, I'd say. I think I missed a part of this talk, but what is our policy that we are optimizing? Uh, so Sam, I'm not sure if you're referring to the policy like policy gradients or like some other optimization methods, but we are actually in this algorithm we are not explicitly training for policy, though our policy is derived from a value function or rather from a distance function. So when we have our distances, we can say, okay, our policy is just choose the next place to go where the distance to the central state is lower, and that's our policy. We are not explicitly optimizing for that, but if we have a correct distances, this policy is optimal. Okay, Renuka, can we learn 333 cube not a hash and look for path of a hash by stopping the fine central state of a hash? I mean, I'm not sure again if I get the question correctly, but we can definitely apply the same method for 333 cube. But I would say if one learns it it really depends on how the states are encoded and how these graphs correspond to each other. But we actually haven't tried learning this function on one group and then transferring to another. That would probably not work really well, especially that our methods are not that advanced compared to the No, so there's still like way to improve, and right now I mean, right now it's not clear if we can come with some like general single models which will solve like any given group. Again, groups are quite rich, and it feels like solving like this, do this group AGI. Sorry for this word, but anyways. Okay, I will can actually show you maybe some um so okay, there is a question, where will the slides be? So first of all, I will definitely send it to Vasily and to Ilya, who helped me to organize this. Yeah, thanks a lot, guys. And yeah, you can ask it from them. And I will also share it with some Telegram chats on our community. Yeah, so if after that you will still be lost and you won't be able to find it, please reach out to our GitHub. You can post an issue there, or like we will try to get it addressed. But I think most people here, they're either coming from Vasily or from Ilya's communities, and then yeah, we can check them out. I can also show for the rest who is here the our Kaggle competitions. We actually have quite a lot. Don't consider they're not like actual competitions. They are more like benchmarks. They're benchmarks for different like groups, for Rubik's cube of different size. For like this is FS. We actually have a competition for Megaminx. I think this is it. Yeah, and if I remember correctly, yeah, recently Vladislav managed to get a better score compared to Thomas Rokitsky's score. Thomas Rokitsky is like he's really good with heuristics. I think he implemented one of these like core algorithms. Yes, so yeah, we are doing Megaminx, and of course you can check tester's notebook here and improve from other guys' methods. Yeah, and here on GitHub there is a list of all competitions we are hosting. So yeah, you can basically check them out yourself. But yeah, my convenience is definitely here. All right, yes. So if any more questions are present, feel free to address them now. I think I will wait maybe for a few more minutes. If I don't see any question, then we will wrap it up. GitHub link, yes, it's here. It's in the slides. Yeah, you can write it down yourself. Yeah. Fair enough that if somebody doesn't have the connection, that yeah, they won't be able to see the chat. Oh, yes, sure. I can type it down. Um, yeah, maybe just. Oops. I can, but the point is that these slides, I don't. I think I need to share this link. I can do. I can see if it's possible. Again, I'm not that much of a streamer, and I don't really watch streams that much, so I don't know if can I post anything to this chat after our stream is complete. GitHub, CayleyPy. Yeah, that should work. Competition list is yeah. I'm a little bit lazy to type this competition list, but it's in the README of GitHub. So yeah. Yeah. Okay. Sure. Feel free to type it here. Yeah. And to the slides. Let's see if I can actually share them. Okay, they are considered to be private, restricted. Okay, yeah. I can actually share the links to the slide. Um, Let me see how can I do that. Oh yeah, all right. I think I can do that from my cell phone. I don't think I have direct connection with this notebook as a phone, but yes, please check if this link actually works. That should be a link for the slides. Yeah, I know that I can click share, but the problem is that then I will like I need I don't have this YouTube YouTube open on my PC, and well, due to some technical reasons, it would be hard to open it there. Yeah, but again, I will share the PDF version of the slides with everyone, like with at least with you guys. Okay, I don't see any non-technical questions here, so I think we're good to wrap it up. Thanks everyone for coming, and thanks for listening. Uh, I will be happy to see you in our competitions and our chats and our CayleyPy community, and let's advance these methods together. Yeah, Vasily and yeah, Ilya could. So please tell me if we can wrap the streaming up. So do we need to stream anything more? Like, yeah, looks like we are good. Okay, then thanks a lot once again, and goodbye, everyone.